this is the day of the JoJo, but if you're not, don't worry about it. So okay, let's see. Okay, so uh, before going to the today's material, I look up my previous video, and then there's some kind of like ambiguous word that they say in this one.
I tried watching yesterday's video and it said it was like shut down because it was too long or something. I don't know if that was just me.
Oh yeah. Oh yeah, that's also another thing is that yesterday video one got like 2 hours, and then when I tried to upload to YouTube, it says and like my internet speed is also convenient, I would say, for like keep re-uploading for like 2 times or 3 times. I tried twice and it doesn't work, so I just upload everything onto CCLE. So yeah, that's also one thing. Put everything onto CCLE. So this is our CCLE class, right? Give it a load a moment. And if you go to the yesterday, and this is the folder, I put all our recording inside here instead of like, going to the YouTube for now, just for now, because it doesn't work. So hopefully you guys understand some of the inconvenient. So yeah, this is gonna be our like recording from the other day that we talked about gradient descent, etc. Right? Hope you guys understand that. From now on, I'm gonna change from YouTube into uploading everything on CCLE instead. Sorry about that. Or if you have any like concern about it, maybe you can email me and I'll try to figure it out somehow. Maybe I put into like some daily motion or something. Maybe I don't know. But if you guys really need it, just let me know. Right? And yeah, let's go back to the last lecture that the last discussion that I said that this is the cost function and it's gradient descent, and I said that try to catch it. It should be the derivative of the cost function. So if I write down like the full definition of it, a gradient descent. So gradient descent, it should be something like this. So it's theta. So I send it theta 0. So this one gonna be the new one. Is equal to theta 0, the old one, minus lambda of derivative of in mathematical term, it should be partial derivative of a cost function over the theta 0, or in English, it's so this one should be learning rate times the slope of the cost function of parameter theta 0. So yeah, just some correction that I want to make, and this also applies to any parameter or any theta or any beta. So like beta, it could be like beta 2, and this is the learning rate, and this is the cost function, and find the slope of that cost function for the beta 2, etc. And then let me also highlight here, and this will be this part. All right, so that's the correction that I want to make, and other than that, I don't think there's anything else that I missed. hopefully. Oh yeah. Uh, so we're gonna start it from here then. So I might go a little bit too far ahead of the lecture, so please bear in mind. But I think that maybe it will be also nice to introduce you guys some of the concept earlier, so that you guys are also familiar when you're in the lecture as well. So we continue from yesterday that I mentioned that use we have some terminologies, and we have underfit, we have overfit, and we have a right at the middle, which is the best model that we want it to be, right? But people also come up with other terms to describe how the model performs. So here are two things. We have bias and variance. So these two, let me use orange instead. So we have bias and variance, and uh, in a term, in like the simple English, I would say it's like the bias is the inability to capture the true relationship, while variance is the difference in cost function between the trained data and the test data. So generally, when people talk about, we have the model that looks something like this. Give me also 1 second to make sure I didn't do it incorrectly. Mhm. Yeah, all right. So yeah, suppose that we have the model that looks something like this, right? And the blue, the one with the blue data is our testing. I mean, it's our training data set, and the green one are the test data, right? And then we make a model that looks something like this square line and the red one, right? And this is our model. And if we do a model, if we create a model something like this, it's gonna be obviously it's gonna be overfit, right? And then when you try to like uh, evaluate its performance with the test data set, it's gonna show that it has it's kind of have high error, or yeah, so-called high error, I would say, or it doesn't really capture the test data set really well. So that's mean that this model doesn't really perform well. So in this one, we can be, the model can also be described as this model is low bias. Yeah, yeah. This one, this model has low bias, but it has a high variance. High variance, right? Because we say that it has low bias. That means that it has less capability to capture the true relationship. So the model says, so ideally our true relationship will look something like this, right? Like some kind of parabola, half parabola. But our bias is quite different from the ideal one. So we're gonna say it has low bias. Well, if you try to see the cost function, so basically you try to look at the distance between the data into the, sorry, should go to the model. So this one is the cost function, which practically the cost is equal to zero. It's equal to zero, right? But this one cost could be like say 100. That's just some number that I randomly come up. And the variance says that it's the difference between the cost function of the cost function between the test data and train data. So it's gonna be some high number. So we say it has high variance. And if you look at the whole thing, the whole picture is that, okay, so then this model is, it is, this model is overfit, right? So this is the also another visualization of how it has how it can be the model can be has a high bias, low variance, which is going to be underfit, or it's going to be overfit, which is it has a low bias and high variance. So the whole point is that we we can say the model is underfit, or it's overfit. But the other way the other way around, we can also say that the model has a high bias, low variance, which means that it's underfit, or it's low bias and high variance, which is overfit. And yes, ideally we want to have the low bias and low variance, so something somewhere around at this point. So it should be somewhere around here, right? Which again, if you also have to keep in mind about the model complexity. If you want to go like to the too high degree, it's gonna the line. Yes, the model gonna capture every data, but then with the new testing data, it doesn't really do well. So then yeah, you also have to like do all types of trials and error to see which one works best, which kind of leads us to the cross validation. But that's also right after this. And I guess any question with the bias and variance concept and really its relation to the underfit or fit. But yeah, otherwise you can also ask me after class or PSR or email me. Yeah. And a little bit recap then, yeah, that since we also get into this slide is that we also have R squared, and R squared in the plain English term is that it's just a way to see how well the model capture the data, the data. Yeah, how well does the model capture the data? And one means that it captured the data really well, but zero means that it's not doesn't really capture the data very well. That's the R squared score. And yeah, if you see Oscars go like super high, you kind of have to raise your eyebrow. Like, does that mean it overfits? But it also have to be part of your analysis that you have and your decision making that you have to um, decide whether you want to keep this model or not. And other than that, I think that's everything that I want to cover from the yesterday like discussion. Let's see. All right, let's come back to the today's discussion and probably also cover for tomorrow lecture a little bit. Yeah, but let's do that. Give me also one moment. All right, so let's come back to the discussion. So this, I guess this is probably a good picture to represent how overfit works, right? You're in a sleep, but then yes, you normally sleep in that pose, but when you try to like move around it, you're gonna fail over the table, I mean the bed. But that's so then is it the correct one? Probably not, right? And this these are the underfitting, the balance model, and overfitting, which we already covered. And yes, so we're gonna cover the cross validation. And our motivation is that we don't know how the model can perform really well, right? And sometimes we're splitting your data into the test data and then the train data, and then so supposedly this is our data, right? And when we train data, which is from the blue star, it's gonna ideally our model should look something like this, right? If you after you train, do all the gradient descent and uh, updating your parameters and everything, should look something like this, right? But then when it comes into the test data, or then this one is validation data. So take, yeah, before that, I should go into the validation and the test data set. So validation normally is used for the the training period, right? So when you train it, you also want to have some kind of measurement to see how about the model perform during the training phase. So we use this validation, and then the test It's like the separate one that you also test the whole model after you finish the training phase. So these are like three different things. But if you really like confused about it, for now you can just say like validation is also the test data. That's also another way to think of it. So yeah. So supposedly that we have our validation data that are the red box, red square, right? So then the red square tells you that since since the data look like this, right? Then it tells that then if you've only like completely remove every training data set, right? And you only have the validation data, you're gonna say, oh, then if you only has the right one, then this is our ideal model, right? But in reality, it doesn't. If you also include the train data set, it doesn't work, right? Because we see that it technically should be this blue line. So, but it should be this, right? So then we have a problem if we accidentally get the test validation data that looks something like this, or the test data that looks something like this, right? So then how can we deal with this? We're gonna introduce the concept of cross validation. Uh, so it's gonna be here. So this is cross validation. Let me just write down. Right. So then the way that we do cross validation is that we have to make sure that every data set is trained is every data set has been used as a train data set and the test data set as well. So it has to be both test and train by. And how do we do this? We're gonna randomly randomly split the data into different chunk, right? And then each chunk is gonna be used as a test data set once. And then once you finish the training model and everything, you're gonna find its error cost or the error value or it's gonna be your cost value, right? And once you finish that, you redo the whole process and train the model with this iteration. You use the fourth one as your test data, and then you keep training with the other four, right? And then you do that, and then you find another, and then you calculate the error value, and and ideally is in reality it should give you a different error, right? But that's gonna be some rare cases that gonna give you like the same one. But yeah, in reality, it should give you the different error. So then you keep repeating that again and again. So this one you're gonna repeat it 5 times by since you split every data set into 5 chunks. So after you get the 5 time and 5 error, you want to find the average error cost of the average error value. And after you get the average one, that's gonna be your uh, error for your model. So instead of having like this one say 0, right? But this one also say like 0.7 and this one like 0.1. You average them all instead of going with the first one and say, oh, that's 0, but that might be like some kind of invalid test the test data set or validation data. So we want to use this to make sure that we receive different data set and trade offer. I receive different test data and you receive hopefully better test accuracy. So far so good.
Wait, how would you code this in? Would you
Yeah,
just put it into a for loop and then kind of iterate it through, or?
yes, yeah. The manually you can use for loop to iterate everything, but sklearn also provide the cross validation for you. So sklearn cross. I think this one, yeah. They also provide the the method for you from the sklearn library, which it tells you like this one. It gives you all the different score for each cross validation. So like this one, it says do it 3 times, right? And then it shows you, okay, if after splitting the test data differently 3 times, it gives us this area, and you're gonna do all kind of analysis within it.
Oh, okay, I see that. Okay, thank you.
Yep. Any other question? All right. Otherwise, let's also do something further than the lecture, I would hope. But yeah, this is going to be hopefully a gentle introduction. But yeah, if you still don't understand, also feel free to also stop me and ask question. I can also like give you a further explanation. And this is like beyond the lecture, so keep that in mind too, if you're like not familiar with the concept. But yeah, let's jump right into it then. So yeah, so some recap. So in uh, in reality, the data doesn't really have the linear relationship, right? So then you would have to have something like something that looks similar like this. So then you would have to build the model that is not like a simple linear regression, but it has to have some kind of higher degree, like to the x to your x to your third or x to your fourth. That looks something like this, right? So that it can like kind of capture the data really well, or this one is gonna be splitting the data into like different boundary, right? So then the problem is that how do you know like which one is the right degree, like, right? We can say like we just do trial and error and then keep changing everything, but is there some kind of math equation that we can simply use it and then hope for the best that it can at least save us some time and save us some work? And it's gonna be some of this type of work is gonna be called regularization. Haha. But actually it spells like that with an L. Anyway, so regularization, right? So let's say this is some example to also recap you with the linear regression. So this one's gonna be something like uh, y is the model looks something like this, right? Y is equal to, I'm gonna use I guess I can use beta, doesn't really matter. Beta 0 plus beta 1 x, right? And this one gonna be third degree, so it's gonna be y is equal to beta 0 plus beta 1 x plus beta 2 x square plus beta 3 x cubed, right? And this one is going to be ninth degree, so it's going to be the same thing, plus b1 x plus etc. to the b beta 9 x to the ninth power, right? And as a reminder, we also have cost function to see how the model perform. So reminder, cost of beta 0, beta 1, so on to beta n, right? So, and yeah, before that, I want to also take a step back a little bit. If you ever see like the cost value or the cost function of, and the notation is that we, yeah, as we see from this model, like, right, we have the beta from 0 to 9, but the other model has like beta that start from 0 to beta 3, right? So we don't really have some kind of ideal number of which one to stop. So then people also just, instead of writing everything down here, we just go with the symbol of parameter, which is the beta. And that's already implied to us that okay, that's the parameters for whatever degrees that there are in the model. So that's also another notation. So I'm going to write down this, the cost value, or this one going to be the mean square error. It's going to be the sum over I of, let's see, in terms of English, it's going to be this predicted of I minus observed of point I, and then you square it. Let me move everything a little bit. Yeah. So yes, that's our cost function, or mean square error, and we have some, and since this is our way to uh, evaluate our model and how will it perform, can it be anything else? As also as like as a thing that I mentioned yesterday, that the cost function is generally looks like this, but it can also be anything else. You can also, like, instead of square everything, you can also put the absolute value between the predicted value and the observed value as well. Or you can take out the 1 over m, or you can put it the 2 in front of m as well. So let's see if we can like try to modify the cost value, the cost function, sorry. If we try to, is there any way that we can modify the cost function and then hope that it can also work out the problem that we are facing, which is finding the right degree. And that's going to be our motivation of learning regularization. And let me get another page. I guess I can just copy everything from my other lecture instead of waste time doing this. Here. Right. So suppose this is our example. Let's see, example. Right. We have our y, which is our predicted. What does the I mean? Oh, sorry, I have a private question. What does the I mean, the cost function? So yes, we can go back to here again. So the notation of I in this one is slightly, yeah, I just remember I slightly put it in a different way from yesterday. But yeah, but the I is that it tells you what are the points of the data. What yeah, which point of the data is your ith one. So like this one can be, say, I says if you substitute with I, then this is going to be your first one. This one's going to be your substitute I with the second one. So this is going to be the second data set, or second data. This is your third, fourth, etc. Right? And then you find the predicted value and the observed value, and then you try to find the cost value of each data set, and then you sum it up, and then the whole thing, you average the whole thing, and that's going to be your cost, the cost function and cost value of your model. Yeah, let me also I can also write down like this one is from him, and I is your I data from the data set. Right? Hope that clears up. Also clears up the notation. Otherwise, you can also stop me, and yeah, I can also go into more detail too, or maybe find another way to explain it. All right. Then let's continue with this. So let me also try to see if I can erase something. Yeah, I can erase this, and then that, nope. Anyway, and that. So yeah, so suppose that our data, our test data, so this is the black X, right? It's gonna be our test data. These two are gonna be test data, and then after you get it, no, not test data, sorry. It's our data. These two are our training data, and then you try to predict, use the model to predict this from this training data. So it's gonna be look something like this, right, from the blue line. But in reality, that's only what we see. So the data, the full data might look something like this, which you're gonna have the X, the red X. This one gonna be your the whole data set, right? But then if you see the whole data set, you're gonna see like, okay, so then I'll put our ideal line, so then should a linear regression should has the line that looks something like the red line, right? Let me also take away the green for now. Yeah, it should look something like this, right? So then we also, but otherwise our training data, it says it doesn't go in the same way as our ideal one, right? So then we would have to also modify it a little bit so that hopefully the line will kind of decrease its slope down to this red line. Right? So we're going to modify our cost function in order to achieve the goal. So let's see, if we modify the cost, and so for this one, it's going to be the cost of theta 1 for now. So let's modify it to be the same thing, 1 over m, and it's the sum of I started from the predicted of psi minus observed of I, and then you square it plus lambda times slope square, or technically it should be parameter square. Technically parameter, but I'm going to use slope just for now so that it is easier to understand. But in general, if you're going to generalize it, it's going to be the parameters. But let's keep it for now, and then I'll talk about the general form later. And you can see that this is our old cost function, and we also add this term, and this term are called penalty term. So this is penalty term. And again, this is our lambda, which is our also another parameter. It's not quite like a learning rate. People just keep using the Greek letter again. But yeah, in terms of this, if you see it, in terms of you have to look at the full context too. Like if you see lambda here with the slope, and then you have some cost function, so then you know that that's going to be our penalty term of lambda, and that you're going to do something with the slope, right? So, but for simplicity, for the sake of simplicity, let's set the lambda is equal to 1 for now. And so let us apply the blue line onto our cost function of this modified cost function, aka regularization. And these are the points that I provided, the point coordinate of the test data. So this one going to be 1 at 1, and then at 2, right? So then this 1 and 1.7, this is going to be here, and then this is going to be 2, 3. Right? So let's find the cost function then. So for example, for the blue line, it's going to be cost function. So if you look at the cost function, the old cost function, you see that the blue line goes through the data set to these two data set perfectly, right? So then we can conclude from here that since it goes past the data set perfectly for this case, then the old cost value is going to be 0. So I'm just going to put in the old cos plus lambda times slope square, which is going to be equal to 0. And lambda, we just set it as 1 for now to see how it works in action. And then you can see slope. So the slope of the blue line is just the coefficient in front of x. So this is just 1.3. So it's going to be 1 times 1.3, and you square it, right? And then when you do all the calculation, you're going to get 1.69. But you can, okay, now you get the cost function. We're going to try to also compare it with another line that looks different from the blue line, and I'm going to give it a green line, which the equation of the green line is y equal to 0.8x plus 0.9, and we're going to find the modifier cost function of this line as well. So in the same manner, the green line, we have let me do that real quick. So in the same manner, we have this one, the cost value, the cost function of the old one, which is going to be yeah, correct. So we have two lines. It's going to be 1/2 times the predicted. So let's see, for the first one, it's going to be 1, right? So what's the first data set? The x-axis for the first data set is 1. So 1, you substitute 1 back into the line value, the line function, which is 0.8. So 0.8 times 1 times 1 is just 0.8, and the 0.8 times plus 0.9 is 1.7. So we go with 1.7 minus the observed of the first one, the first data set, which is gonna be this value, is 1.7. So we use that in here. Wait, do I do it incorrectly? Let me double check my number. Should be 1.7 blah, blah, blah. Yeah, 1.7. Yeah, well, anyway, I made the notation kind of slightly wrong, but anyway, let's go with that. I can just do the calculation at the moment. At this time, this also doesn't matter. All right, and that's our first data set, which is this. And then you go into the second data, which is 2 and 3, right? So you predicted, you substitute 2 into the x again. So it's 0.6 plus 0.9 is 2.5 plus 2.5. And then minus the observed value, which is here. For the second one, the observed value should be 3. For the training data, so with this one, right? So it's gonna be 3, and then you square it. And you also have the penalty term. So you plus lambda, and lambda is equal to 1 times the slope, which is the coefficient of x, so 0.8, 0.8 square, right? And that's gonna give you, I'm not gonna do the math in my head. We should just use calculator, shall we? Give me one moment to do this. 0.5 times and that. So that's gonna give us 0.5 square and plus 0.8 square, which gives us 0.765. And this is our cost function. This is a cost value for the green line, which is this green line. And from the visualization, we can kind of see, right, that like the green line is slightly closer to the ideal red line instead of the blue line, if you look at the whole data set, right? But we can see that, yeah, the blue line kind of capture the training data well, but it doesn't really capture the whole data set, while the green line doesn't capture the the training data really well, but it captures the whole data set, including the training and testing well. So that's going to be regularization, is that we try to, instead of going to the full on like crossing every training data, we kind of modify it so that it's slightly not have the cost value of all data to 0. Is kind of like gets you a little bit more, and we add a little bit more off from the training line, right? And then you add some penalty term, and this penalty term is gonna tells you gives you a better line that captures the whole full data. So like here we can see green cost is less than blue. And again, every time that we do build the model, we want to get the minimize. We want to get the minimum cost value instead of go for a higher one, right? So that it can capture the data well. And we can we can also expand this into other dimension, because right now we're just working with 2 dimensions, right? But in reality, there are lots of dimensions, like 10 features or more. So I'm gonna generalize this cost function or regularization into a higher dimensions, and it's gonna be,
Oh wait, I don't know whether you've already stated this or not. Wait, so for lambda, will it always be equal to 1?
no,
Or
that's
just the example that we gave for now?
yeah, that's just an example that we are doing. Go for it for now. It
Mhm.
it could be changed to like a million or 1,000. It doesn't matter. But the point is that if you say, yeah, I think that's a good question. It can also be lead to other questions as well. Like say if you change the lambda to 0, what does it mean? So then it's gonna be the cost. This is the old cost value, the old cost function plus 0 times slope, right? So slope square. So then this thing is gonna have like less. It's gonna be meaningless, right? So yes, you can change to anything, but if you want to like make the line kind of does not capture the training data set really well, and hopefully get all of the data instead, you will change the lambda into some random number, like 1 or 10, 100 or something like that. But if you don't care about it, you can set it to 0, and then it goes back into the old cost function that we learned earlier.
Okay, I see. So
Yeah.
lambda is just something that you would usually just make up, usually, right?
Yes.
Okay.
Yes. And I think it's gonna go into a further slide, but let me double check if I have that. Maybe I can also, yeah, I can also explain this in this. So regularization, right? As we also discussed, and you also asked that we do, if we set the lambda, and then what if we set the lambda into like 1,000,000, right? But remember that the goal is that I can also write here. Goal, we want to minimize the cost function. Or maybe I could go with cost value, right? And then the cost value is that it's going to be, let me get this. I can go with another page. that and here. So yeah, remember we have the goal is that we want to minimize the cost value, and it's gonna be some ugly notation, but yeah, I'll try to explain a little bit bits by bits. That it's gonna be lambda times slope square, and the whole thing we want to minimize it. I'll just say it as min for now. And let me ask questions like, if you set lambda to, say, suppose we set lambda to 1 billion, right? If you're going to minimize everything, and suppose that this is just a constant number or some constant number, and we just don't care for now. If we want to modify the cost value to be as minimum as possible, then what would the slope value be? It will also be like a super low number, right? So maybe I can also give you concrete number like what's the value of slope to make the cost function, cost value equal to 1. So what would that be? That will be 1 over, that will be 1 over million, right? So that's just like some random number that I come up to have a concrete example. It could also be something else. So, but if you look back, slope, if the slope, then that means that you must change the slope to something else, to some small number. And we can also see from here, right? You see that the slope of the first line that we had earlier is 1.3, and now this one we're gonna have 1.8. So it's gonna capture the data. But if you set the lambda to like some high number, in order to minimize everything, if you have high number, then you're gonna multiply it by some low number so that it kind of balances it out, and then hopefully you get the minimum value, right? And so in order to do that, we must set our slope into 1 over million, and in the some kind of line algebra, it's gonna look something like this, right? The slope of line slope of like 1 over million is gonna look something like super horizontally, but not exactly. This is like in the scale of like 0.00001 or something, right? And this is like 1, I don't know. Yeah, just some like visualization. So what does that mean in the big picture? In the big picture, if you try to use regularization, that means that you're gonna try to make the slope of the graph kind of goes horizontally, and that means that you don't. That means that the model you will let me think of the sentence correctly, because my understanding is that you will not use that parameter to explain the data if you set the slope into like 1 over 10 to the 9 or 1 over billion. But let me see if I can like paraphrase that to something else. But yeah, I guess just remember it that if you set the slope, set the parameter very high, that means that some of the parameter will be set into like some very low number, and then that means that parameter will not contribute that much to the whole cost value of everything. But I should also go with the whole cost of everything to be like, so then.
Nathan,
Yeah.
one question. Is the slope here the slope of a point, or it's the slope of the whole function?
It's going to be a slope of our line, our regression line.
Of the whole linear regression, not just the point you're measuring, not just not I slope, not the certain data.
Well,
Because
yeah, you go ahead.
No, I'm listening.
Okay, yeah. So this thing is just calculating the distance between the line, right? Just distance between the line and the observed data point, but
Yeah.
it doesn't really tells you, it doesn't tell you like the slope of it. It doesn't have any relationship inside here. Well, maybe you
hmm
use it for calculation, how do you get the prediction line, but instead we use our slope inside here instead in the penalty term.
So
Slope
this, so,
model.
mhm.
Yeah.
But then how would implementing the slope, how would implementing the slope increase the loss function if the slope is just like it fits like if the slope fits well, but it's just a very high slope? Wouldn't it need to be like, wouldn't it need to be the slope of like a certain part of the function to tell if it's if it's fluctuating all over the place, or if it's a good fit instead of overfit?
Let me see if I can like general, I can like give it a simple term. Maybe I can try this. So so do you remember the whole goal of regularization is that we don't want the model to be overfit, right? But if you make the model, like you said, if you make every parameter capture the data really well, right? So then you're gonna get some kind of overfitted data. So it's for example, you look at the equation here, right? So if you look at this, you have x to the cube, x1 to the cube, right? But then if you look at this equation, where is x1 to the cube? It doesn't have it. So how do you kind of like remove out the x cube in here? You set the parameter, which is x, this one theta 6, to be as close to 0 as much as possible. So that way, like some small number. So since this one gonna be small number, right? Small number, which is the theta 6 times something like constant, I guess. You're still gonna get the small number, and if that kind of goes with the small number, then hopefully also get reached to like 0.00001, and then we can just leave it out. And when you leave out this x to the cube, you're gonna get this model. So that's like the whole big picture of why we are doing regularization, and we try to like make the slope, make the graph not capture the data set really well. So hopefully that it doesn't make it too overfit. Does that kind of related to your question?
I kind of get it, but it's mainly on that particular penalty term. Like, how does that particular penalty term that you showed us like affect like a particular function?
Oh yeah. Maybe I can
Because
also.
like, all right, can you go back to your example with the like one page to the left? Like for that one, if the data trended more upwards in the graph, then wouldn't that penalty term make it so that the better line of best fit was had a higher cost function?
Let's see. Are you talking about like if you say supposedly you draw this line, or is that like
if the data itself was like, if the green and the blue were underneath it instead of over it?
So maybe you can go like this.
Yeah, so if they were underneath the red instead of over it, then wouldn't that make it so that the blue line has a higher cost function because its slope is higher?
Yes, but that's also related. That's also related to the lambda that you also have to set to. So I don't have
so you
like
could have a negative lambda if.
Yeah, generally we don't use negative lambda. You can have like positive number, but I could say like I don't have the full number to like have you show example, right? So, but for now we can go like, so if this case, just this case, it's gonna be for lambda 1, right? But if you set lambda to like 100, then the maximize supposedly the minimum cost value is gonna be something like this new blue line or the purple line. But if you also like change it to like 1 million or 10K, it's gonna the line that's gonna give you the minimum cost is gonna be this one instead. So it's also like related to how you choose the lambda to be how much, and then that with that much with that much of amount, when you calculate everything and you try to optimize by finding the minimum cost value, so similar like this, right? It's gonna give you another slope instead.
Okay, I think I kind of get it.
Yeah, if you don't understand, don't worry about it. It just work. So normally, yeah, the algorithm is like it just work. It's either it just work or don't worry about it. So yeah, you have to consider like many factors. Like okay, if you set the lambda, so like as the same thing, right? If you set the lambda to 0, like earlier we have just this, and then you have the train data, just looks like this, right? And then you just make the line go over the data. So just make the line. Yeah, Ethan, we can say.
Oh yeah, so in the code, are you able to like change the lambda like for the function? Like I know that you kind of can like just use like pre-implemented like things, but is there like a way to change the lambda so you know you can get better?
As far as I have worked on this, I've never tried it, but generally, yeah, maybe you can if you have to like do everything manually. Yeah, you would have to set the lambda by yourself and do other stuff. But in terms of this course, I don't think you would have to like concern about it. It's just this thing is basically just some kind of technique so that we hopefully don't get overfitted data. But yeah, you can definitely do that by yourself. I don't really remember if to see if they have linear regression. What's it? Regularometer. Yeah, fitting set, normalize, positive, rank singular. But yeah, my short answer would be sorry, I don't really have any answer for that. You could either manually do it by yourself, but yeah. Yeah, can't really say that I am familiar with anything that you can like modify it by yourself. But generally, yeah, if you look at this one, they also provide the rich regression for you, which is the regularization that we are doing, and it's gonna automatically kind of like adjust the lambda for you, and then tells you that which slope that you can like remove it out from your data, so that it will not be overfit. Yeah.
All right, thank you.
So yeah, let's go back to here and then. Oh yeah, and let's go back to that via the whole thing that we do regularization. We call it regression. So it's gonna be so the cost function of that is gonna be cost of again. Yeah, we could go with beta again. It's gonna be let me check 1 OM. So it's gonna be the mean square error, the same thing. Maybe I can go with this mean square error or MSD plus penalty term, which is equal to 1 over m. That's going to be your mean, and we're going to sum it all over the prediction. I'm just going to write pred as a prediction and observe OPS, and then you square it plus lambda of theta. Sorry, it should be beta 0 square plus beta 1 square plus dot until beta n square, which if you also generalize it, it's going to be the same thing. Plus lambda times sum of each beta by itself over I, so beta I, and you square it. And that's now that's the regularization of our cost. Yeah, that's going to be our regularization, which we call it ridge regression for this case. And again, the whole point of ridge regression is that if we set the lambda to some high value, we're going to hope that if we set the lambda to some high value, in order to get the minimum cost value of everything, right, you're going to have to modify the parameter, aka the slope of that axis or slope of that feature. So if you get the slope down, slope of the feature like to the very almost horizontally, that's gonna kind of like that's gonna tells you that the model doesn't really use that particular feature as the best model, and hopefully with that it kind of reduce some kind of complexity, and it will not be too overfitted, like the first one that like this example that we remove it the x cube, so that we hopefully get this data, this best fit line instead. If you don't understand, don't worry about it. Yeah, that's the whole main point, that we introduce some kind of new cost function so that we hopefully don't get the overfitted data. You don't have to like understand all of the math, everything behind it. It just work. So yeah, that's the concept of regularization. Yeah, this is main takeaway. So we want to find a way to make the model underfit, so that we can, well, probably to be more specific, like not to make the model not overfit, so we can get higher testing accuracy, or even if the training accuracy is slightly lower. And I don't know. Yeah, let's push like 5 or 10 more minutes, and then we'll take a break, and then we come back to the Jupyter notebook, etc. So you see that the cost function we put in a square, right? But people also it also becomes some kind of research field, and then people also try to do, instead of doing a square, you take the absolute value and the square, right? That's also another called lasso. So we use absolute value instead of squaring the parameters. And if you compare with the ridge regression, which is the one that we also went over with the equation, and we have lasso, and again from ridge we square the parameter, and lasso we take absolute value. But if you use the ridge regression, it's kind of like make the parameters close to 0. Meanwhile, the lasso is just makes the parameter reaches 0, or basically you kind of exclude the useless parameter. While the ridge regression, it just makes it close to 0, but not. So that you hopefully you use that feature for our model prediction, instead of like exclude everything out. And we'll have some kind of visualization also from the Jupyter notebook after, right after this. But yeah, other than that, you have yeah, you guys have any questions or concern? But if you don't understand, yeah, that's just something that people come up with, and then they found out that this is another way that you can also make the model less overfitted by removing some useless feature, or useless some useless degree.
Yeah. I have a question.
Yeah, go ahead.
So why do we square the values or absolute values? Take the absolute value of like the parameters if they both in the end achieve the same thing, right?
Mhm.
So what's the difference between the two?
Yeah. I see you see the slide ahead of me. Haha, no, I'm kidding. Yeah, that's a good question. And this is like some visualization that I also it's kind of stimulated, I guess, from YouTube. So this, let me go with this. This is some of the example that they do, and I just grab it. So if you this the top one is gonna be the regression, which is the slope square, but the bottom one is lasso, which is the absolute. And I'm not really have like a concrete example, right? But sorry about that. But for the all kinds of research and all kinds of like experiment, we can see that if you try to make the you want to find the slope of the model of the cost function of each model, right? So you can this is going to be our cost function slope. And when you try, as we also mentioned, that we try to get the lowest cost value. If you're gonna get the lowest cost value, it's gonna be something like this, right? And this one is gonna give you around like 0.2 instead, 0.2. But on the other hand, if you do the absolute value, it will magically give you the 0 as your minimum, as your minimum value. And that's gonna be your slope of that of your particular feature, and then you basically exclude that. So that's like the magic of the math, which to be honest, I don't have like a full concrete example that I can also show you. But yeah, it just works, and don't worry about it. Yeah. But that's something for you to be aware of how can you like make the model not overfit. Yeah. But yeah, that's the difference, is that even though you try to increase the lambda so that the slope goes to the small value, right? It will also just go as far as like 0.2 or 0.1. But if you take an absolute, it will automatically get to 0 instead. Yeah. Other than that, that's the discussion. But we still have the Jupyter notebook after this. Yeah. From this, everything that we learned, we use cross validation to average the models across all trials, and we average the models and the error instead of accidentally pick the so-called invalid test data that makes some kind of huge error value. And we just reach our lasso regression to lower the slightly lower training accuracy, but gets the higher test accuracy. Kind of okay. Hopefully, don't worry about it too much. It's not, I can't say that it's not on exam because I'm not sure how exam gonna work, but there's some concept of it that you use regularization to make the model not overfit. It seems like I repeated like 10 times, but yeah. That's about it. And let's take 10 minutes break and then we come back to do the Jupyter notebook then.
Okay. Yeah, so I just want to come here and try to see everyone. So I just have like small suggestion, right? Because right now we are in a small group. So if everyone can turn on your camera, like in later sessions, probably that will be very helpful, okay, for like a better interaction. Yeah. Hello.
Yeah, you can turn on the camera.
Hello.
In the big classroom, there's no
see.
way for me to see everyone, right? But I think it's a slightly different situation. That's also a reason like we want to put everyone into smaller cohort. Okay, yeah. Thank you for turning on your camera. Nice to see you. Of course, it's a break. Okay, so yeah, you can do whatever you want. Okay, great. Thank you. Bye.
Thank you, Professor.
Can I not be the only one with my camera on? Please, guys.
Now you can turn it off. If you guys can just like unmute yourself and then talk to me, that's also good enough.
Okay.
I don't know.
Thank you.
Yeah, because I don't know, my mindset, the mindset for me is that I kind of okay with like being similar to a live streamer, you know, like you can just read the chat and then have interaction to it. It's also, that's also fine.
Our
I don't,
streamer.
yeah. Just don't forget to like donate me or something. No, that's I don't want to get into court by like it's so called extorting money from
Are you gonna
state.
make a Twitch channel eventually? Or have you already?
Yeah, I have gamer microphone, so why not? Let's go. But yeah, people feel it differently. But yeah, if you ask me, I don't really care about it because I also feel like I'm also in your guys' situation. Like, yeah, sometimes I'm not really comfortable to like open your camera. Right? I'm just like lie down like this. Like if I'm gonna stay like this and open camera, it's gonna look kind of bad, look kind of sus. I don't know. So just like, yeah, it's okay. I rent a lot, but yeah, we still come back to 225. forgot to put my mic down. Haha. I'm not a pro gamer, I guess. Is it clear now?
Yeah, if you have to be a
Yep.
Twitch streamer, you
Alright.
gotta have your sets already.
Sorry. Yeah, I should have got like a
It's okay.
Blue Yeti mic or something. But yeah, let's come back to the example. Imagine nothing happens. Yeah. All right. So I guess we'll come back, and when we are in the break, I can think of some example of how you can get the ridge regression, and then this is your optimal line, right? And or your optimal regression, your model, and you're gonna have some kind of coefficient that looks really small. So if it still exists in the equation, you just say if x3 is going to be equal to 1, right? So then the predicted value is going to be some kind of value plus 0.008 or something. So then it shows that the feature of x3 still has some contribution to the predicted value. Meanwhile, if you do the lasso regression, the final equation will look something like this, and the coefficient of x3 is going to go to 0. So something like looks like this, which is going to give you the minimum cost value, right? And if you set it to 0, that means that implies that x3 doesn't contribute anything to the equation at all. So we can simply just so-called remove the useless feature out of our line instead of having it, and then it may potentially cause some overfitting. So that's some example, and we're gonna see in the Jupyter notebook right after this. And let me grab the link and switch screen as well. Here. If you guys don't see screen or it's like some kind of gray window or anything, also you can let me know too. And let me get the share link in our continue output. Yes. Oops. And where's chat box? Here. All right, you guys sign up to the Google account and then make a copy of that. And let's see. Oh yeah, there's also the second version in case that like you don't want to simply run everything. Let's see. Oh gosh, dang it. Let me switch tab. The thing on top of Zoom is just takes away everything. Let me get that. So this is also another version that has all the blank modules. Let me grab the link, the second link of that. Let me see. Anyone can this? No, not edit. Sorry, you guys. I don't want you guys to accidentally edit everything. Change permission. Yes. Or no. You know what? I'll just make a copy and then I'll send you guys a link of the copy instead. Sorry about that. Give me one moment. Let me change back to. Oops. Huh. It changed back somehow. It's okay. I can just talk to the other TA then. Let's go to. All right. Again, this is the blank version. Let me get that. Yeah, that's the second one. You can also feel free to make a copy of it, and then instead of like watching me run everything, you can also try to figure it out and also like play around with the data as well. But for me and for us, I would say just simply also just watch me and then see see my or hearing my explanation. That's also enough. But yeah, let's go with this. So again, regularization and model selection. We have our everything. Construct a model, and we talk about model usage. How do you find the model and then test against our data? And for model selection, it's also kind of similar to the things that we talk about regularization, like how can we select which particular necessary feature that we want to include inside of it. And let me take a quick glance of it. Yeah, we also mentioned about how we can use square score to kind of evaluate our model performance. And this is going to be our variable selection sample. So let me double check with this. Yeah, it's just a graph, and we want to like have a quick look into it on how it works with the data that could be like have some contribution, or we can like simply delete it. Let me just download that. And actually, I already have that. I can also just drag it from my link real quick. Let me close some unnecessary tab. Yeah. I'll be honest, this is gonna be a little so-called boring. Sorry, yeah, but this because the whole thing is pretty straightforward. You just run it and kind of like, but the whole point is that we want to see that you can, instead of just doing everything, doing all the calculation, there are also some of the method that helps you identify which feature are necessary for you, or which are not necessary that you can also exclude it out. Let me try to import that again. Why is it not working? Let me refresh. Let me upload it again real quick. And yeah, you run everything, and let me see. I can change my path, just the file name. That should be good. Let it install some of the necessary library real quick, and then whoops, I think this is 6th tab, no, last tab. Forgot to import. Let me take that, grab that. Yes, I forgot to import the necessary libraries to do all the work, and then we import the CSV file, which is here into the data. And if you run it, the hit commands again, we want to see how the data looks like. So you can only just show the first 10 of it. You can see there are scores and prerequisite takens, blah blah blah, and you can also just run the info method to see the data type and how many entries or how many rows are there. And this is just to plot the graph, and we can kind of look at the graph and see that how spread of the data comparing to the percentage score, because we want to predict from the percentage. We want to predict the percentage score, but we want to see what would happen for each feature if we plot it out, and if it spread it too, does it spread too much? Does it have some kind of line relationship between the feature and our predicted column? So this one score, this one prerequisite taken. So like ID number, you can also suspect from the column name that, yeah, probably doesn't really have any relationship between ID number and the percentage score. So it's kind of like, and when you visualize it, it kind of spread out. So you can also kind of think, maybe I can also just drop that feature, hours study, and score. They also has some relationship. So that's other thing that we noticed from this plot. So again, when you have data, we want to split it into a test and training data set, right? And this one, we just use the linear regression model to do the prediction. And then now this one is the also another method for us to kind of select only the necessary feature. Is to sequential feature selector. I don't have like a full definition of it, but maybe sorry to say this, but you might have to also look up by yourself. And that's also something that I'm probably not gonna memorize anyway, to be honest. I can just also look up to see how it works. But yeah, basically the whole point is that it will select the features that are necessary for us and can be contributed to the array score, to the test score. So it's gonna give us the array that shows that the first feature doesn't really matter that much. So we only take the true value, which is I think true. Let me check. That's gonna be not number. I believe it's prerequisite taken. Wait, let me double check with the. I don't remember exactly which column would that represent to. Let me just see. Should be 1/3. No, it should be false as the column. You know what? Let me check. Let's see together. That's how we always works. Let's kill it and see what does it return with the get supported method. Get support, get MS or index integer of features selected. And parameter, if true, return will be a integer, sorry. No, that's not it. And what is the return value? And index that selects the return features from a feature. If indices is false, this is a Boolean array of shape, blah blah, in which and if element is true, if and only if its corresponding is selected from retention, is if the index is true, input feature. So yeah, so basically true is the one that we want to keep it, and false are something that we can drop. And let me check. Maybe I kind of like too irresponsible if I say like, you guys can also kind of see that, yeah, it will choose the parameters or the column that are necessary for us by doing all kind of regression, and then see if there's any drop feature. So if you see transform, next train, shape, it's going to give you only 2 columns. Right? I feel like kind of mumble or ramble a lot, but anyway. Let's go to indexation. It's a cross-validation. Well, we will have the regularization, which is more towards the things that we learned earlier. But yeah, cross-validation is also some kind of the thing that we also mentioned, that we want to split the data into the test section and then train section, and when we run it, and we will see that what's the number that the split method works for us. So let's see. Can scroll up, loading this in. My data didn't go through. Loading this, okay. So yeah, the way that I did for loading data is that I just simply upload it here. And it will be goes through here, and then I use the CSV, and then just the file name. Or another way again is that you can upload it to your Google Drive and then do all kinds of this from Google Colab, import Drive, and then run it. And I think this is the previous one, but then I modified the path of it. So like, in computer, you have a path from your top folder into your subfolder, and then down and down until you reach the file. But this one is just already enough to tell you that, okay, if you have a path, it can kind of infer from here that, okay, so then this is the path that we are working for. So that should be enough. So far so good. Hopefully that clears up. Yeah. All right. Let's see. Yes, we have cross validation. This one, we just gonna show the index of it. So like there are for X, we have four elements. There's the first one, this 2, 3, 4 is the second one. This also the third one, and this are the fourth one. We just print out the index just to show you that it kind of split up into the train data set and test data set, so that when you're working on a project or right after this, yeah, you're gonna go work on the project, and then you're gonna do the split data, or so, and then you would have to calculate the error from this, and you keep switching the test data set and train data set over and over, and you average the score. It's due to import statement, I believe. Oh, Neil, I'm not sure. Neil and Nilan, I'm not sure. Import statement. Is there any like what's the error that I think it should show some kind of error? Does it tells you any specific error?
For mine, it says that file not found error. It happened. I imported the pandas, the numpy, and the matplotlib. However, even then, it still said that file not found error.
I think you have to move the file into your drive.
Oh, wait, do I have to download it like straight to my computer as well? Or?
Yeah, I think you have to make it go to your drive before
okay.
that works.
Okay, let me try that.
Yeah, download it. Yeah, you can try that, and then you also get back to me later and see how it goes.
Okay, let's try that one more time. We'll actually move this to Google Drive as well.
But yeah, let's go back to it. Meanwhile, we can also mention a little bit about cross validation, and I want to see if we can also change the splitting into like 4. I believe that also works. 4 K4. So like this one. Now you just go. Let's see step. Can you scroll? Let's implement step forward. Yes. Let's see, where is it? Is it here? No, it's not. I'm blind. Can you guys help me? Feature select. I don't see it. Okay. Yep.
Okay, I figured out, by the way, how to do the letter to you.
Nice. But yeah, if you also you can also get into the first link that I sent, if I remember correctly. That's also have the full answer from it. But yeah, this one, as I mentioned, is a sequential feature selector. So basically, it just drops some unnecessary column or feature. But I'm not exactly sure if we modify the indices of the feature, which one does it tells us? Because we have X train, Y train. But yeah, anyway. So for your cross validation, you can kind of see like if you change the parameter of and split, so you're gonna split it into some x amount of time, like this one 4. I think we can do 5. No, it can't because we can exhaust all of the data already, since we have only have 4 as my maximum, so maximum is 4. But if you split it into 3 times, you will randomly get you the chunk of data, so that each time we can use this data set to train the model and test on it, and then we will repeat that again, test on it, save this error score, test on this, and train on this, and then test on the second one and the third one, and then you save your error score, and then you average them out to see how well the uh, linear regression, for example, works on this data instead of using other errors like neural network, I guess. Yeah.
Nathican.
Mhm.
For some reason on the now let's implement our step forward feature selector, I get an error when trying to import the sequential feature selector.
Oh yeah, you also have to write this line because yeah, short answer, you have to run this command too, and then the last line it should show point 0.24.2, because the long answer is that the sklearn version of Google Colab is 0.22.2, but you need to update it.
Okay, thank you.
Yeah, because I think that's only included in the newest version for the sequential features later. So yeah. So yeah, run the module and then come back, and then it will hopefully work. Or you might have to like refresh the Google Cloud to make it work. But yeah, that those are the cross validation, and we have the regularization. Yes, we have lasso and ridge. So let's see them in action. That's our lasso, and we import the lasso again, and we have x data and y, and then we split it out. So if you look into the data, the data has 2 coordinates. So basically, it's a 3D data, kind of. Yeah, 3D data with 2 features, and y is going to be your uh, observed value. So you have 2 features, and then you run it, and then you split it up to test and train, and then you fit it up, and it gives some score, right? But you run the lasso. You run the lasso regression. You run the linear regression plus the lasso. So basically, lasso regression. This is our L1, which is the lasso object. You run it, and then you also can write down L1 dot coefficient to get the coefficient of x1 direction and x2 direction, x2 and x1 axis and x2 axis. And if you get that, you're gonna see that the coefficient will become to 0. So that means that the coefficient of x2 doesn't contribute much uh, to our model. So that's how lasso works, and you can kind of see like, yeah, it just magically works for us. So that's probably the good thing that we can use coding. But yeah, it's also like it will also be good if you're like familiar with the basic math concept of it too. That the lasso can make the coefficient of x2 goes to 0. Meanwhile, we have regularization or ridge regression. But yeah, which gonna be, instead of taking the absolute value for the lasso we take absolute value. Ridge we use square, right? So we just call it ridge, and you can take, when you run it and you fit it, and you print out the coefficient, it's gonna be slightly different. But yeah, we can see that the coefficient of x1 direction and x2 are 0.24, And you can see that it's the slope between here is 0.4. You can say that X1 has more contribution to the final value, to the predicted value than X1 in this model, which is the ridge regression. So you can see it's kind of, maybe I can also try like 0 to see how it works too. It's going to give us almost close to 0. Yeah, let us experiment with it. So alpha like 200, see how coefficient will be. Yeah, it will keep decreasing. So as we also kind of discussed, if we keep increasing the alpha or the penalty term, which is the lambda, it's gonna make the slope slightly, not slightly, but more into the horizontal, or going to like the small number, and it will so-called has less contribution to the predicted value. So we can also go like some number. I don't know. It's gonna give you something like this. Yeah, 9 times 10 to the negative million. No, -6, which is, yeah, quite a small number. But if we change it to 1, it shows that the model, our best fit model, is gonna be y equal to 0.2 x1 plus 0.2 x2 plus this intercept. So yeah, that's pretty much about it for the Jupyter notebook that we have for you guys. I don't think there's any, well, oh no. Let's see. Can I ask you guys' opinion? I have one last thing, which is to show like some kind of idea that you can do the project, which might take around like 5 or 10 minutes. Do you want me to just give a final push for 5 or 10 minutes and then we can call it a day, or do you want to take like a couple minutes of break?
To be honest, I don't really mind. Anything
Me
that would
either.
really help. Yeah. Because if we can get through today, I don't really mind. Yeah.
All right.
Just a final push seems good.
Yeah. Okay. Sounds good. So then yeah, you guys can play around with the notebook, and I think that's pretty much for that. And we see some of the probably project idea, and yeah, I'm gonna give you some of the project idea, and hopefully you guys can have some idea on what you can potentially do with your project. But the specs of the project has not come out yet, so I can't really have a final say for this. Yeah, maybe I can like introduce you guys to some of the website or some of the stuff that you can do, and then you guys can like take home and then trying to maybe look up later, or like trying to think about it, and maybe we can come back like tomorrow or like the Friday, and then you can like kind of propose some of the idea to professor or to me, and then I send it to professor, etc. So yeah, this project, I'm a weeb, so why not just go with anime or anything? So I just do the anime recommendation for myself with my my anime list account, which is the website for keep tracking the anime that you like and you have watched. But yeah, that doesn't matter. The matter is that I used the data science algorithm to make the recommendation. So yes, I don't want to go much into the details. I can just go give a little bit of what I did for my things. That yeah, I import the data and everything, and then do other things that we also did earlier. Look at the data and then try to like modify the data a little bit. And I do the one-hot encoding to the data, and then the features become all the anime lists, and then only one for the one that we have watched or we already scored, and blah blah blah. We do all the kind of manipulations and lots of data manipulations, not gonna lie. And yeah, after I got the final data, I just use the nearest neighbor model, which we're gonna learn it later, maybe next week. Yeah. So basically, I just find the closest data, and after I find the closest data, I just print out the nearest data to me, and when I get that, yeah, these are the nearest data to me, like 20 nearest to me or 50. Yeah. And after I get that, I look at each data or each user and then average score and everything together, and then bam, these are the list of the anime that I have not watched, and maybe I can potentially watch it later from based on other users' watch history or their rating. So yeah, I can go with the of 10 years neighbor with the highest average score. So like people put 10, but after as soon as I see like okay, most of them have only come up just one, so I can also just go with the highest frequency or most mentioned. So like we can say Death Note, but technically I already read the manga of it. But yeah, I went on a tangent. Anyway, we can also just go with the see which one has the highest frequency for around my data point, and then see which one could be interesting to me. And yeah, that's one of the idea that you guys can probably come up with and maybe modify a little bit. And please don't try to like copy me everything. Okay, I want you guys to also like kind of struggle and also learn along the way too on how can you deal with some kind of problem. And I probably send this out as an email later today, but I might have to also discuss with the professor or TA too on how like what's the project gonna be like. Yeah, we'll see. So I also come up with some of the ideas that you guys can probably do it as your final project too. Anime recommendation, I already did that. Movie recommendation, also similar to mine. And there's a movie lens data set, which they also provides all kinds of data set for you. I think this, they also have the, let's see, machine learning. So yeah, you can go to grab something like this, a small one that has 100K ratings and from 600 users, and then you can also try to see the data and then input your own data on your own movie, your favorite movie, and then see if you also come up with some kind of recommendation. And maybe you can also work with work with your own image recognition. So like maybe later you'll get an experience like how can you like classify your handwritten letters or handwritten digits. Maybe you can also come up with your own data set and try to classify it by yourself to see how well can you capture uh, your handwritten or maybe some kind of other image. I don't know. Maybe you can try like capturing, try to classify if what you are drawing is a circle or square or triangle. Maybe that's also some idea that you can think about it too. And the last thing is anything from Kaggle. So in case that you don't know, Kaggle is the website for data science community that they provide all kinds of data set for you, and you can also join it for the competition. And let me see, I believe we also have the homework of Airbnb, and maybe we can also use that. Yeah, so for example, if you search anything that may be interested you, like you can go with the Airbnb data and see if they have any interesting data that you can use. So like you can go look into the file and then see if what are some features that they have, what are, and you can look at it. They have the host name and you have, they shows all the neighborhood, etc. And I believe, yes, they also have the price. So you probably want to predict the price based on every features, but which technically is going to be in your homework one as well, I believe. Yeah. And or maybe something like, I like soccer, so why not just go with football? player. Market price, I believe. Not that. I believe I have solid ones. But yeah, price prediction. You can see like okay, there's some player. There's a player, and then there's nationality, and what are the leagues that they play, the club that they play for, and then they have the price onto it. Maybe you can predict the price of the player if a certain player play for this club, and they're this nationality or their which position are they playing, something like that. So that's for you to look up from Kaggle.com. That's also another idea that you can also come up with and maybe explore it around and talk among your team. And maybe we can split you guys into a team like tomorrow. Or, so yeah, maybe sometime tomorrow or later Friday. Yeah, but yeah, those are the main 4 things that I can come up. Or you guys can do anything else too. It's like, as far as I know, it's kind of free game for you guys. You guys can do anything, but maybe Professor might come up with a guideline maybe later tomorrow. I'm not so sure, but yeah. The point is that explore around and try to have fun with it. Oh yeah, and one last thing. Maybe you guys can also ask me later about the project or homework or how I implement mine, or if you want to talk about anything about me, that's also fine too. But yeah, let's take a quick look at the homework one, shall we? Let me change my screen real quick. So we have that. Let's go to my download. Oopsie, that and that. And so you're gonna have 2 parts of homework one, part 1 and part 2. Part 1 is gonna be slightly more work. Well, definitely more work. Okay, I also have done this and kind of challenging. So maybe you should try to start that earlier. Part 2 is just simply run it and then print the result. But let me also just import that onto Collab. Let me drag that real quick. Close that. Yeah. Let's see. Let me see if there's so view, expand sections. All right, so let's try that. Try to do some stuff with this. So yeah, this is divided into two main sections. The first section is just an example of how you can do with the how you can do with the data set. You have all kind of setup and you import data. Yes, this one just showed all the example of how you can shows the data, and this one uploaded the data, etc. And then another time we do some analysis with the data. So like say this one is you do the housing and check on the feature ocean proximity of your, I believe it's Airbnb at New York. That's the same one that we also watch. Look at it later. No, not later, earlier. Yeah, and this one you also look at it and see what if in that feature, what are some of the values within it. You see like how do you have a minimum value for each column right here, and then you kind of visualize it to see how the data spread out in that feature, right? And yeah, basically that's also something that you can also read it by yourself and try to get to understand on what's going on with each part. But my point is that you don't have to memorize everything and understand everything. You kind of want to manipulate some of the code in here to make it work within your own data, which is going to be the second part of this. This one, just visualize it and everything, and you draw some correlation data here, right? And everything else, and it's gonna come down to like here, and then once you get all the data manipulation and visualize data, drop some feature and all, you will have to select the model and train it. And then you train it, and then you print out the error score from here, right? And that's like the example that you can look for, and which is to predict Airbnb based on a feature. I don't think that's the one. Let me check. Let me check from the folder. Let's see. I believe it's dataset housing. Sorry, let me double check if I say it correctly on which one we're gonna supposed to use. This one use dataset housing.csv, so it's not that. Yeah, it should be in the Airbnb folder, and this one AB New York City. So all of this data, right? So you're gonna work with this data, and you're gonna try to predict the price, which is this column. And to be honest, you can kind of like follow everything from the first section step by step, and then make some data manipulation by yourself, or to make it work on your data, because that data, the first data set is not the same thing as the second one. So you do all the thing, you visualize it, and you do some plotting, blah blah, and you prepare your data. So you do some like impute any missing feature, or maybe like dropping any feature that might not be necessary, and you fit the model, and you print out the score, the mean score error from your data. I don't think the performance of the model is matter that much. I think the first one is want you guys to get familiarized on how do you deal with the data science, deal with the data set, and how you can use data science to at least get something out of it, rather than make like the best prediction. So hopefully like, you guys can play around with it and copy from Google. I don't want to say that, but yeah, that's probably legit the most obvious one, that you can kind of like have to like look up from Google and then copy the things that people do and then adapt it to your own code. But yeah, that's like the whole overview of the first homework. And I think that's pretty much for today. I don't think I have anything else. If you guys don't have anything, you guys are dismissed. Otherwise, I can stay here for a bit to answer any question.
Thank you.
Yep.
Thank you, Nathan.
Yeah.
Thank you, Nathan. See you.
Thank
Yep.
you.
See ya.